Welcome to Sleep Science Top 1. Tonight, we explore radiation as a physical system, not as a story meant to comfort you, but as a measurable process that quietly governs how energy moves through nature. This evening, we shall meander through one of the most misinterpreted phenomena in the entirety of nature. One will embark on a journey to uncover radiation, not as an object of fear, but as a timeless, constant companion that has influenced every moment of existence since the dawn of time. So settle in, adjust your pillow, let your breathing slow, and prepare to uncover the quiet glow of the universe around you, humming with an unseen energy that links every star to every atom, including those that compose you. The tale unfolds not amidst peril or calamity, but rather in a realm of tranquility. It starts with illumination. Each morning, as one awakens, sunlight pours through the window. The light, that warm golden glow that fills the room, is a form of radiation. The soft embrace of warmth against your skin is a form of radiation as well. It is electromagnetic radiation, traversing 93 million miles of void to reach you, arriving in a steady wave of energy that has traveled for approximately 8 minutes and 20 seconds from the surface of our sun. Yet, what truly enhances its beauty is this. Radiation has existed long before modern times, not as a product of human ingenuity, but as a natural phenomenon. It represents a core principle of how energy traverses the cosmos. It has existed since the dawn of time, since the initial spark illuminated the cosmos 13.8 billion years ago. Let us take a moment to reflect on that number, 13.8 billion years. For that duration, radiation has journeyed through the vastness of space, transporting energy, generating light, producing warmth, sculpting galaxies, and ultimately enabling the emergence of life. At this moment, as you recline and absorb these words, at any moment, your body is immersed in several distinct natural radiation fields, each with a measurable intensity and origin. The device in use emits a small quantity of electromagnetic radiation. The walls surrounding the individual hold faint traces of radioactive elements, such as potassium-40, which release soft particles into the environment. Cosmic rays from distant exploded stars quietly pass through your body, thousands of them every minute, like invisible threads that connect you to the far reaches of the universe. At these background exposure levels, long-term population studies show no measurable increase in health risk, for there is a truth that must be grasped from the outset. Radiation is not an agent of harm by itself. It is a physical mechanism by which energy leaves one state and enters another. It is the light, weaving its way through the cosmos. They are particles spinning away from unstable atoms. It reflects how physical systems reduce excess energy while conserving fundamental structure. The allocation of energy, the processes of transformation, creation, and sustenance. Allow me to share the essence of the word, for each word carries its own delicate narrative. The term radiation originates from the Latin word radiare, signifying to shine or emit rays. In 1760, the term emerged in English, carrying with it a straightforward meaning: the emission of energy. Neither peril nor ruin, merely release. The mere act of projecting something outward resembles the way light radiates from a candle flame. The ancient philosophers, despite lacking our contemporary insights, perceived a profound truth regarding light and heat. The Greek philosopher Empedocles, who lived around 490 before the Common Era, suggested that light was a phenomenon that traversed and moved through the vastness of space. He envisioned flames pouring forth from the eyes. He misjudged the mechanism, yet he grasped the fundamental truth. Energy moves. In the year 1604, centuries after, Johannes Kepler examined the diminishing nature of light over distance, developing concepts about radiation that would ultimately contribute to the understanding of energy dispersion in space. His work exhibited a mathematical precision, radiating a sense of tranquility in its implications. Energy adheres to established rules, operating within defined principles, and disperses in ways that are both predictable and comprehensible. Let us journey back even further to the fundamental atoms that constitute all that surrounds you. An atom, as one might recall from their school days, is primarily composed of empty space. If one were to enlarge an atom to the dimensions of a football stadium, the nucleus would appear as a tiny marble nestled at the heart of the field. The electrons appeared as minuscule dots, circling in the uppermost reaches. What lies in the gaps? Void. Nothingness. Void. And yet, this largely vacant edifice is bound by forces so immense that they shape the very essence of matter. The nucleus, that small marble at the center, holds protons and neutrons within its confines. Protons possess a positive charge. Neutrons possess no electrical charge whatsoever. In a realm where particles are compressed into a space so minuscule, it challenges the limits of conventional comprehension. At this point, the narrative unfolds in a captivating manner, evoking a sense of calm and reflection. The protons within a nucleus are expected to push away from one another. All of them possess a positive charge. Just as like charges repel, this principle stands as one of the essential tenets of electricity. When two positive charges are placed in proximity, they repel one another. And yet, somehow, within each nucleus, these protons remain united. At times, there were dozens of them, all confined within a space countless times smaller than the width of a human hair. The force that binds them is known as the strong nuclear force. It stands as one of the four essential forces that govern the natural world. It possesses immense strength, yet its effectiveness is limited to very close ranges. When protons are brought sufficiently close, the strong force triumphs over their electromagnetic repulsion, securing them in a stable arrangement. However, there is an important point to consider. Some configurations lack stability. Certain arrangements of protons and neutrons align seamlessly, akin to puzzle pieces that have discovered their rightful positions. These nuclei may remain unaltered for billions or even trillions of years. They experience a sense of joy, if one might choose to describe it that way. They maintain equilibrium. These nuclear configurations remain statistically stable because binding energy exceeds internal repulsive forces. Alternative combinations seem to miss the mark. They possess a subtle flaw, an imperfection that leaves them a touch unsteady, reminiscent of a Jenga tower that has reached an excessive height. The nuclei exhibit instability. They possess radioactivity. When a radioactive nucleus ultimately sheds its excess energy, relinquishing its instability and evolving into a more stable form, this process is known as radioactive decay. It emanates a hidden brilliance. It is a profound change, an atom shedding its energy to emerge as something different, something more harmonious, something more serene. The revelation of this phenomenon unfolds as a soothing narrative, serving as a reminder that even the deepest truths can emerge subtly through moments of attentive observation and patience. In 1896, a French physicist named Henri Becquerel found himself immersed in the study of phosphorescence, the soft glow that certain materials release after being illuminated. He carefully wrapped several photographic plates in thick black paper to shield them from light, then placed uranium salts atop the protected plates, intending to expose them and observe the outcome. However, the skies over Paris grew overcast. With each passing day, the sky remained shrouded in clouds. Becquerel, anticipating the arrival of sunshine, casually placed his experimental setup in a drawer. As the sun finally broke through and he prepared the plates, anticipating an absence of discovery, he was met with something extraordinary. The plates lay bare, revealed to the world. The uranium salts had etched an image through the black paper, despite having remained in a dark drawer all along. The uranium, he understood, was radiating something inherently, not due to the influence of sunlight, but simply because that was the nature of uranium. It emanates a glow. It radiates a hidden brilliance, not derived from any outside influence. but emanating from the very essence of its atomic composition. Becquerel made a groundbreaking discovery in the realm of natural radioactivity. Not long after, Marie and Pierre Curie, toiling away in a repurposed shed in Paris, delved deeper into the mysteries of this peculiar phenomenon. They meticulously processed vast amounts of uranium ore, subjecting it to boiling, dissolving, and crystallizing repeatedly, all in pursuit of the most intensely radioactive substances. In an environment that might appear severe by today's standards, they maintained a composed and systematic approach as they successfully isolated two new elements. One was named polonium, in honor of Marie's homeland, Poland. The other was named radium, derived from the Latin term for ray. The radium emitted a soft glow. In fact, it radiated a noticeable glow. In a dark room, a sample of radium salt would reveal its presence by emitting a faint, ethereal light. It emanated a blue-green glow, soft and peculiar, reminiscent of moonlight transformed into substance. At times, the Curies would make their way to the laboratory under the cover of night, drawn by the sight of their radium samples, illuminating the darkness. Marie later reflected on these visits with a sense of wonder and beauty, portraying the faint light as one of the most exquisite sights she had ever encountered. They remained unaware of the lurking dangers. They were still unaware of the complete significance of their discovery. Yet, they had unlocked a portal to the atomic realm, and what awaited them was not disorder or ruin, but a profound metamorphosis. Elements transforming into different elements. Radiation has existed since the dawn of time. The unfolding of nature's profound processes is unveiled. At this moment, it is worthwhile to reflect on the insights we've gathered up to this point. Radiation is energy traversing through space, or particles released from unstable atoms. It has existed within the cosmos since time immemorial. It exists within the embrace of sunlight. It lies within the stones that support your steps. It resides within the very atoms that constitute your being. The revelation of radioactivity was not a creation, but rather a keen observation. Radiation was not a creation of humanity. It was observed, quantified, and gradually comprehended. Now, let us delve further. Let us delve into the various forms of radiation. Not all radiation is created equal, and grasping these distinctions will illuminate why certain types can pass through you harmlessly in vast numbers, while others demand our vigilant focus. As scientists embarked on their detailed exploration of radioactive materials, they observed that the emissions exhibited a peculiar behavior. Some were effortlessly halted by mere paper. Some could pass through paper, yet were halted by slender metal. Nevertheless, some were able to traverse significant obstacles. In the early 1900s, a physicist by the name of Ernest Rutherford conducted elegant experiments aimed at unraveling these differences. He positioned radioactive materials close to magnetic fields and noted the way the emissions curved. Some curved in a single direction, some curved in the opposite direction, some remained completely straight. Through these observations, he discerned three unique types of emissions, which he aptly designated with the initial three letters of the Greek alphabet: alpha, beta, and gamma. He discovered that alpha radiation was made up of relatively heavy particles that carried a positive charge. Subsequent research revealed that alpha particles are, in fact, helium nuclei, consisting of 2 protons and 2 neutrons bound together. When an unstable nucleus emits an alpha particle, it is, in essence, releasing a minuscule helium atom devoid of any electrons. In the vast realm of radiation, alpha particles emerge as gentle giants. They are quite substantial when compared to other forms of radiation, and they can be readily halted. A sheet of paper halts their progress entirely. A mere few inches of air halts their progress. The outer layer of your skin, composed of dead cells that are in the process of being shed and replaced, halts them completely. If a small sample of alpha-emitting material were held in your hand, the alpha particles would be entirely absorbed by your skin. preventing them from reaching any living tissue. They are unable to break through. They are unable to delve deeply. They are excessively large, overly charged, and readily absorbed by matter. The sole risk associated with alpha emitters arises when they are inhaled or ingested, allowing them to enter the body and directly irradiate delicate tissues. Yet, from an external perspective, they appear innocuous. Beta radiation is made up of much smaller particles, specifically electrons, or occasionally their antimatter counterparts, known as positrons. These particles are released during the transformation of a neutron into a proton within an unstable nucleus, or the other way around. The particle released takes with it the surplus energy. Beta particles have the ability to penetrate paper. However, they are halted by a thin sheet of aluminum or even a substantial piece of plastic. They have the ability to travel slightly greater distances in the air compared to alpha particles, potentially reaching a few feet. However, they are still relatively simple to shield against. When beta particles make contact with the skin, they have the potential to breach the dead outer layer and reach the living cells beneath, which could lead to damage. However, the discussion revolves around low energies in this context. Subtle impacts, effortlessly handled, with straightforward measures in place. Gamma radiation stands apart. Gamma rays are not particles in any sense. They are photons, packets of electromagnetic energy, akin to visible light, yet possessing significantly higher energy. Energy is released when a nucleus transitions to a lower energy state, all while maintaining its count of protons and neutrons. Gamma rays possess the ability to penetrate deeply. They move seamlessly through paper, plastic, metal, and even your body. To protect against gamma rays, one requires materials that are dense and sufficiently thick. The effectiveness of lead is attributed to its density. Concrete proves effective due to its ability to be made thick. Water functions to some extent, provided there is an ample supply. However, it is crucial to grasp this point. Even gamma rays can be controlled. Even gamma rays adhere to established principles. Their intensity decreases as the distance increases, indicating that if one were to double their distance from a gamma source, the intensity would reduce to a quarter of its original value. When the distance is tripled, it reduces to 1/9. Separation and protection. These serve as the essential instruments for safeguarding, operating effectively due to the adherence of radiation to established physical principles. It does not pursue you. It does not pursue you. It emanates effortlessly, dispersing in accordance with geometric principles, and being absorbed based on the characteristics of matter. Now, let's discuss a topic that may initially appear daunting, yet reveals a sense of comfort once it is fully grasped. Let us discuss the reality that you, in essence, possess radioactive qualities. Indeed, you, the individual resting there, absorbing these words, striving to drift into slumber. At this very moment, you are releasing radiation, soft illumination, innocuous radiation. Yet, there remains radiation. Here is the reason. The body is composed of potassium. It serves as a crucial component, vital for nerve function, muscle contraction, and numerous other biological processes. Approximately 0.017% of all natural potassium consists of an isotope known as potassium 40, which exhibits radioactivity. With a half-life spanning 1.25 billion years, potassium 40 reveals a fascinating aspect of time's passage. This indicates that, beginning with a specific quantity of potassium 40, half of that amount would undergo decay over a span of 1.25 billion years. The decay unfolds at an excruciatingly slow pace, remarkably tender. Yet, it occurs. The typical human body holds approximately 140 grams of potassium. That indicates you hold approximately 17 milligrams of potassium 40. In your body, this minuscule amount experiences approximately 4,400 radioactive decays each second. 4,400 times each second. Within your body, a potassium 40 atom undergoes a transformation, becoming either calcium 40 or argon 40, while emitting a beta particle or a gamma ray during this remarkable process. And at these exposure levels, population-scale studies do not show measurable health effects. They have always been fine. These decays have been occurring since before your existence, and they will persist long after you have departed. They exist within the backdrop, woven into the very essence of life on this planet. You also possess carbon-14, a radioactive variant of carbon formed in the atmosphere as cosmic rays collide with nitrogen atoms. All living organisms take in carbon-14 from their surroundings, including the food they consume and the air they breathe. An average human encounters approximately 3,700 carbon decays every second, with a rate of 14 decays per second. Within you, there exist minuscule traces of uranium and thorium, derived from the food you consume and the water you drink. Within you lies a trace of radioactive hydrogen, known as tritium, present in minuscule quantities. Each of these elements adds to your unique personal radioactivity. Should one recline beside another, equipped with an exceptionally sensitive radiation detector, the latter could indeed quantify the radioactivity emitted by the former. One could tally the particles and photons radiating from your being, and the sum? Approximately 8,000 decays occur each second. 8,000 transformations of unstable atoms into stable ones. And yet, everything is well. You are in good health. This radiation poses no harm to you. It is merely a subtle background noise of atomic change, so gentle and so evenly spread throughout the body that it bears no significant impact on one's health. This is comforting for several reasons. It suggests that low levels of radiation do not inherently pose a threat. It signifies that our bodies have adapted to a naturally radioactive environment and possess mechanisms to mend the slight harm that natural radiation inflicts. The presence of radiation alone does not inherently signify danger. What holds significance is the dose, the energy, and the passage of time. The significance lies in the quantity, the type, and the duration. Imagine it as a source of comfort. A soft glow from the fireplace envelops the room in warmth and solace. The same fire, when touched directly, would inflict pain. However, the presence of fire is not the issue. The dosage, the closeness, the duration of exposure, these elements hold significance. Radiation operates in a similar manner. The sunlight that caresses the face is a form of radiation. The X-ray, a tool that allows a doctor to visualize a fractured bone, is a form of radiation. The radiation emitted by a smoke detector, ensuring your safety during sleep, is indeed radiation. Each dose varied, each purpose distinct, all within reach and comprehended. Now, let us shift our focus to another facet of the narrative surrounding radiation. Let us explore the origins of radiation in the universe, for grasping its beginnings allows us to perceive it not as an anomaly, but as an essential element of nature's intricate design. At the outset, illumination emerged. This language lacks a poetic quality. It pertains to the study of the universe. Approximately 13.8 billion years ago, the universe emerged from an event known as the Big Bang. In the initial moments, the universe existed in a state of extreme heat and density beyond comprehension. Energy and matter could transform into one another. Particles emerged and vanished as the entire universe was engulfed in a brilliant surge of radiation. As the universe expanded and cooled, the radiation followed suit, experiencing a transformation alongside the cosmos. In the present day, that ancient radiation continues to permeate the universe. The cosmic microwave background is what we refer to, and it is indeed detectable. When one tunes an old television to a channel devoid of signal, it is revealed that approximately 1% of the static displayed on the screen originates from ancient radiation, the lingering remnants of creation, continuing to envelop us even after 13.8 billion years. This radiation, now incredibly weak and cooled to just a few degrees above absolute zero, permeates the surroundings. Every cubic centimeter of space holds thousands of photons from the Big Bang, journeying through time, conveying the narrative of our universe's inception. Then appeared the stars. In the early days of the universe, approximately 100 million years after its inception, the first stars began to shine brightly. They were grand, radiant, and fleeting. Deep within their cores, under unimaginable pressures and temperatures, hydrogen transformed into helium, helium into carbon, carbon into oxygen, and continued its journey through the elements of the periodic table. Every fusion reaction emitted energy as radiation. The radiation surged outward, battling against gravity, preventing the star from succumbing to collapse. It was a delicate equilibrium, a choreography between the overwhelming pull of gravity and the boundless push of radiation. As the initial stars depleted their energy, they erupted in supernovae, scattering their enriched remnants across the cosmos. This material, infused with elements denser than hydrogen and helium, would ultimately give rise to new stars, planets, and in time, you. However, this is the crucial element for the narrative. A significant number of those heavy elements, formed within the cores of stars, possess radioactive properties. They emerge from the cosmic chaos of a massive star's explosion, infused with the essence of uranium. The uranium possesses radioactivity from the instant it comes into existence. It isn't that anything went awry. The uranium, possessing 92 protons tightly packed within its nucleus, inherently lacks stability in its most prevalent forms. Radioactive elements should not be classified as pollutants or contaminants. They're stardust. They're the ash of stellar furnaces. They're part of the natural inheritance that came from the death of ancient stars. When our solar system formed 4.6 billion years ago, it formed from a cloud of gas and dust that contained radioactive elements. These elements were incorporated into the planets, including Earth. They've been here from the beginning, slowly decaying, releasing heat that keeps Earth's interior molten, driving plate tectonics, creating the magnetic field that protects us from solar radiation. In a very real sense, radioactive decay keeps our planet alive. The heat from decaying uranium, thorium, and potassium in Earth's mantle and core is what drives convection currents deep underground. These currents move the tectonic plates. Plate tectonics creates mountains, recycles ocean crust, regulates atmospheric carbon dioxide, and makes Earth habitable. Without radioactive decay, Earth's interior would have cooled billions of years ago. The magnetic field would have died. Solar wind would have stripped away the atmosphere. Life, if it had ever emerged, would have been extinguished. So radiation isn't just something we tolerate. It's something that made complex life possible. Let's think about another source of radiation that surrounds us constantly: cosmic rays. Cosmic rays aren't actually rays. They're particles, mostly protons, traveling through space at nearly the speed of light. Some come from the sunday, some come from distant supernovae, some come from the violent hearts of distant galaxies. These particles slam into Earth's atmosphere at tremendous energies. When they collide with atoms high in the atmosphere, they create showers of secondary particles. Some of these particles make it all the way to the ground. They pass through buildings, they pass through mountains, and yes, they pass through you. Right now, as you lie there in the darkness, cosmic rays are passing through your body at a rate of about 10,000 per hour. These particles travel through you as if you weren't even there, barely interacting with your atoms, leaving only the faintest trace of their passage. Most cosmic rays don't interact with your body at all. They pass through the spaces between atoms, or through the empty space within atoms, emerging on the other side, without having done anything. Occasionally, one will strike a nucleus in one of your cells, creating a tiny burst of ionization. Your cellular repair mechanisms fix the damage, usually within minutes. Life on Earth evolved with cosmic ray background radiation. We're built to handle it. At sea level, cosmic rays contribute about 0.3 millisieverts per year to your radiation dose. If you live in the mountains, it's a bit higher because there's less atmosphere above you to shield the rays. If you live in Denver, Colorado, for instance, cosmic ray exposure is about double what it is at sea level. And yet, people in Denver are fine. They're healthy. Studies have found no increased cancer risk from the higher cosmic ray exposure. The dose is so low, and our bodies are so resilient that it simply doesn't matter. When you fly in an airplane, you're exposed to even more cosmic rays because you're higher in the atmosphere where there's less shielding. A flight crew member who flies regularly might receive an additional 2 or 3 millisieverts per year from cosmic rays. That's about the same as a chest X-ray or two. It's been studied extensively, and while there's some evidence of very slightly increased cancer risk for crew members, it's a tiny effect, and it's complicated by other factors, like irregular schedules, disrupting circadian rhythms. The point is that radiation exposure from cosmic rays, even the enhanced exposure at high altitudes, is generally not a significant health concern. It's background, it's natural, it's something we've evolved alongside. Now let's drift closer to home. Let's talk about the radiation in your house, in your neighborhood, in the places you go every day. Your home is built from materials that came from the Earth, and the Earth contains radioactive elements. The bricks in your walls might contain small amounts of uranium and thorium. The concrete in your foundation definitely does. The granite countertops that some people have in their kitchens can be more radioactive than other types of stone because granite sometimes contains elevated levels of uranium. Does this mean granite countertops are dangerous? No. The radiation levels are low. The exposure is continuous, but mild. It's like the difference between standing outside on a sunny day and standing under a heat lamp. The dose matters. Some buildings are more radioactive than others, simply because of the materials used in construction. The famous Grand Central Terminal in New York City has walls made of granite that emit enough radiation to set off a detector. If Grand Central Terminal were a nuclear power plant, workers there would need to monitor their exposure. But it's not a power plant, it's a train station, and the millions of people who pass through it every year are fine, because here's a principle worth understanding. Radiation exposure is cumulative, but it's also healable. Your body has mechanisms to repair DNA damage. These mechanisms work constantly, fixing damage from radiation, from chemical exposure, from errors in DNA replication, from countless sources. At low dose rates, the repair keeps up with the damage. The net effect is essentially zero. It's only when the dose rate becomes high enough that damage accumulates faster than it can be repaired that we see health effects. And the threshold for that is much, much higher than natural background radiation. Let me tell you about a place called Ramsar in northern Iran. It's a beautiful area on the coast of the Caspian Sea, known for its hot springs. The hot springs bring water up from deep underground, and that water is rich in radium. The radium has accumulated in the soil and rocks over thousands of years. People have lived in Ramsar for generations. They farm the land. They drink water from wells. They live in houses built from local materials, and their annual radiation dose from these natural sources can be more than 200 millisieverts per year, which is about 100 times higher than the global average. Studies have been conducted on the people of Ramsar to see if this high natural radiation causes health problems. The results? No clear evidence of increased cancer rates. No obvious health effects. The people of Ramsar are, as far as can be determined, just as healthy as people living anywhere else. This doesn't mean that radiation is harmless at all levels. It means that low dose rate, chronic exposure, even at levels far higher than normal background, may not cause the health effects we would predict from studies of high dose rate acute exposure. The human body is remarkably resilient. Adaptation is possible. Repair mechanisms work continuously, And context matters in ways we're still trying to fully understand. There's a similar story from Kerala, India, where monazite sand on beaches creates areas of elevated natural radiation. People have lived there for thousands of years with no apparent ill effects. And another from Yangjiang in China, where background radiation is 3 times the global average due to thorium in the soil. These natural experiments tell us something important. They tell us that radiation at low levels, even levels higher than what most people experience, is not necessarily harmful. They tell us that our bodies can cope with radiation exposure when it's part of the natural environment. Now, let's talk about something that might seem counterintuitive. Let's talk about the fact that radiation can be useful, even beneficial, and that we use it every day in ways that make our lives better and safer. When you go to the dentist and they X-ray your teeth, they're using radiation to see through your cheek and gums to the bone and teeth beneath. The X-ray dose is tiny, about 0.005 millisieverts, equivalent to about 12 hours of natural background radiation. But it provides valuable information that helps keep your teeth healthy. When you get a chest X-ray, you're receiving about 0.1 millisieverts, roughly equivalent to 10 days of natural background radiation. In exchange, doctors can see your lungs, your heart, your ribs, and diagnose conditions that might otherwise be invisible. More advanced imaging, like CT scans, delivers higher doses, maybe 1 to 10 millisieverts, depending on the type of scan. That's equivalent to a few months to a few years of background radiation delivered all at once. But CT scans can detect internal bleeding, diagnose cancer, guide surgical procedures, and save lives. The key is that these medical uses of radiation are deliberate, controlled, and justified. The benefit of the diagnostic information outweighs the tiny risk from the radiation exposure. Doctors follow the ALARA principle. As low as reasonably achievable, they use the minimum dose necessary to get a useful image. In the early days of X-ray technology, people didn't understand the risks as well. X-ray machines were used casually, sometimes in shoe stores to check how shoes fit. Children's heads were X-rayed frequently to treat ringworm. Radiologists would hold patients during X-ray procedures without any shielding. We learned from those mistakes. We studied the effects. We established safety standards. And now, medical radiation is one of the most carefully regulated uses of radiation that exists. Every X-ray machine is tested and certified. Every procedure is justified and documented. Radiation workers wear dosimeters to monitor their exposure. Pregnant women are asked about pregnancy status before X-rays because developing fetuses are more sensitive to radiation. All of these precautions exist because we understand radiation. We know its risks. We know how to minimize those risks. And we know that when used properly, medical radiation does far more good than harm. Beyond medicine, radiation has countless other beneficial uses. Smoke detectors in homes use a tiny amount of americium-241, a radioactive element that emits alpha particles. These alpha particles ionize air in a small chamber. When smoke enters the chamber, it disrupts the ionization, triggering the alarm. The amount of americium in a smoke detector is minuscule, about 0.3 micrograms. The alpha particles can't penetrate the plastic case. Even if you dismantled a smoke detector and held the americium source directly against your skin for hours, the dose would be negligible. But that tiny amount of radioactive material, sitting quietly in a device on your ceiling, could save your life by alerting you to a fire. Millions of homes have smoke detectors. They've prevented countless deaths. And the radiation risk? Effectively zero. In food safety, radiation is used to sterilize or pasteurize certain foods. High-energy gamma rays, or electron beams, possess the ability to eliminate bacteria, parasites, and insects in food, all while ensuring that the food remains non-radioactive. Spices undergo irradiation to diminish microbial contamination. Certain fruits undergo irradiation to prolong their shelf life. Ground beef is occasionally subjected to irradiation to eliminate harmful bacteria such as E. coli. The process does not render the food radioactive, just as shining a flashlight on an object does not cause it to emit light on its own. The radiation moves through, accomplishing its task of interfering with microbial DNA, and ultimately leaves no trace behind. The safety of food irradiation has been thoroughly examined and affirmed by health organizations across the globe. It serves as a method, akin to pasteurization or refrigeration, aimed at enhancing the safety of food consumption. In the industry, radiation finds application in numerous ways. The welding seams in pipelines undergo X-ray examinations to identify any defects. Radioactive isotopes serve as markers to monitor the movement of materials within intricate systems. Radiation-based thickness gauges play a crucial role in verifying that sheet metal or paper maintains the correct thickness throughout the manufacturing process. Radiation has been employed to enhance the quality of materials. Radiation can enhance the strength and heat resistance of plastics through the process of cross-linking polymers. Irradiating gemstones enhances their color, resulting in the rich blue hue of London blue topaz. These applications arise from the fact that radiation serves as a tool. It represents a type of energy that can be guided, managed, and utilized to address challenges. When utilized with care and appropriate safety protocols, it poses no greater risk than electricity, heat, or any other type of energy we control. Now, let us turn our focus to a topic that may evoke greater feelings of unease: nuclear energy. Nuclear power stands out as one of the most contentious uses of radiation. Upon closer examination, it reveals itself as one of the most captivating instances of humanity's ability to harness the atom. At the core of a nuclear reactor lies a straightforward and refined process. Uranium atoms, particularly uranium-2, 3, 5, are prompted to undergo fission. Upon the absorption of a neutron by a uranium-2, 3, 5 nucleus, instability arises, leading to its division into two smaller nuclei. This process results in the release of energy along with additional neutrons. Those neutrons can subsequently collide with additional uranium atoms, leading to their fission, which releases further energy and generates more neutrons. When the conditions align perfectly, a continuous chain reaction unfolds, where each fission event sets off a series of subsequent reactions. The energy unleashed during nuclear fission is immense. The splitting of a single uranium atom unleashes approximately 200 million electron volts of energy. At first glance, it may not seem significant, but when you consider that fissioning a single kilogram of uranium-235 unleashes energy equivalent to burning 3 million kilograms of coal, the magnitude becomes clear. Within a nuclear reactor, energy is released in a manner that is carefully regulated. The chain reaction is meticulously regulated through the use of control rods, which absorb neutrons and decelerate the reaction. A coolant, such as water, flows through the reactor, taking in the heat. The heat is harnessed to produce steam, which powers turbines, ultimately generating electricity. It bears a striking resemblance to a coal plant, in fact. Each generates heat, utilizes that heat to produce steam, and employs steam to drive turbines. The sole distinction lies in the origin of the warmth. Within the confines of a coal plant, the process unfolds through chemical combustion. Within the confines of a nuclear plant, atomic fission unfolds. However, a significant distinction exists in the byproducts. The combustion of coal emits carbon dioxide, sulfur dioxide, nitrogen oxides, mercury, and various other pollutants into the atmosphere. The emissions play a significant role in climate change, acid rain, and air quality issues, resulting in the deaths of tens of thousands of individuals each year in the United States alone. The process of nuclear fission results in the creation of radioactive waste, necessitating meticulous management and storage practices. However, it does not emit anything into the atmosphere during standard operation. Free from carbon dioxide, sulfur, mercury, and particulates, the waste is solid, contained, and capable of being isolated from the environment. At this moment, one might ponder various thoughts. Nuclear waste. That seems quite frightening. It seems to radiate a green hue, possessing the power to transform anyone who approaches it. However, the truth is far less sensational and considerably more controllable than what mainstream narratives suggest. Nuclear waste manifests in various forms. Most of it, approximately 90% by volume, consists of low-level waste. This encompasses items such as protective clothing, tools, and equipment that have come into contact with trace amounts of radioactive material. The radioactivity remains at a level that allows this waste to be securely entombed in shallow repositories following several decades of storage, permitting the decay of short-lived isotopes. Intermediate-level waste encompasses items such as reactor components and chemical sludges resulting from reprocessing. This waste necessitates protection and more cautious handling, yet it remains manageable with existing technology. The most formidable type of waste is high-level waste, encompassing spent nuclear fuel. In a reactor, the fission of uranium results in an intricate blend of radioactive isotopes. Certain ones deteriorate rapidly, within a matter of days or years. Some possess half-lives that extend into the thousands or even millions of years. The spent fuel, once extracted from the reactor, remains highly radioactive and continues to produce considerable heat for many years. It requires several years of storage in pools of water to cool down, after which it can be transferred to dry cask storage, where it remains in large steel and concrete containers, cooling passively and safely isolated. The cumulative high-level nuclear waste generated by all nuclear power plants across the United States in the last 6 decades could be contained within a space equivalent to a football field piled approximately 10 yards high. In the United States, coal plants generate approximately 130 million tons of solid waste annually, a significant portion of which is laden with toxic heavy metals and even trace levels of radioactive substances from naturally occurring uranium and thorium found in coal. The issue surrounding nuclear waste lies not in its quantity, but in its enduring presence. Certain isotopes found in spent fuel will pose a danger for millennia. This indicates a necessity to consider storage over durations that extend far beyond the usual human planning perspectives. However, there is a source of reassurance. They understand how to accomplish this. Geologically stable repositories possess the ability to effectively isolate waste from the environment for an extensive duration, spanning hundreds of thousands of years. Finland is in the process of constructing a repository known as Onkalo, which is hewn into bedrock 500 meters beneath the surface. The rock formation has stood the test of time for billions of years, and it is destined to endure for millions more. The waste shall be contained within copper canisters, meticulously crafted to endure for a minimum of 100,000 years. The canisters will be encased in bentonite clay, which expands upon contact with water to form an impermeable barrier. The tunnels will be filled in and closed off. The site will bear a mark to caution those who come after, and then, without human interference, the waste will remain undisturbed, buried beneath the surface, gradually breaking down, cut off from the surrounding environment. While it may not be flawless, it certainly offers a viable option. It can be considered a less concerning issue compared to the release of carbon dioxide into the atmosphere, which lingers for centuries, or the disposal of coal ash into ponds, where it has the potential to contaminate groundwater. Accidents have, of course, occurred in the realm of nuclear power. In 1979, 3 Mile Island experienced a significant incident. In 1986, Chernobyl faced a catastrophic disaster. And in 2011, Fukushima encountered a major crisis. These names hold significance. These instances embody genuine failures, actual releases of radiation, and tangible consequences. However, it is essential to examine what transpired in each instance, as grasping the specifics aids in comprehending both the potential dangers and the impressive safety history of nuclear energy as a whole. In Pennsylvania, a partial meltdown occurred at 3 Mile Island. An unfortunate blend of equipment malfunction and human oversight resulted in a coolant loss within the reactor core. Approximately 50% of the core has melted. Yet, the containment building, that robust concrete and steel fortress encasing the reactor, fulfilled its purpose. Nearly all of the radioactive material was successfully contained. The radiation released into the environment was minimal, comparable to the exposure from a chest X-ray for those residing in the vicinity. No fatalities, no harm, no discernible health impacts. The incident prompted significant advancements in reactor design, operator training, and the overall safety culture. The moment served as a catalyst, prompting a reaction from the industry. The situation at Chernobyl was significantly more severe. The reactor design was fundamentally flawed from the outset, missing a proper containment building. In the midst of a haphazardly organized safety test, the operators deactivated safety systems, leading the reactor into a precarious condition. The reactor entered a state of prompt criticality, signifying that the chain reaction surged at an exponential rate. In mere moments, the fuel ignited, sending the top of the reactor building soaring and revealing the core to the open air. The initial explosion resulted in the tragic loss of 2 workers. In the days and weeks that followed, firefighters and plant workers battled to contain the disaster, with many tragically receiving fatal doses of radiation. In the immediate aftermath, 31 individuals succumbed to acute radiation sickness. A radioactive plume drifted across Europe. Countless square kilometers fell victim to contamination. Countless individuals found themselves in the midst of evacuation. The long-term health effects remain a topic of debate. Yet, estimates indicate that there may be a few thousand extra cancer deaths in the coming decades due to radiation exposure. The event unfolded as a disaster, yet it stemmed from a distinctly flawed reactor design managed within a framework that valued output above safety. The Western reactor designs, characterized by their robust containment buildings and inherent passive safety features, were not susceptible to failure in the same manner. The Fukushima incident was the result of a natural disaster. A magnitude 9 earthquake struck off the coast of Japan, setting off a colossal tsunami. The reactors at Fukushima experienced an automatic shutdown in response to the earthquake, yet they required ongoing cooling to dissipate the decay heat generated by the fuel. The tsunami, which came roughly an hour following the earthquake, inundated the area and rendered the emergency diesel generators inoperative, the very systems intended to supply backup power for cooling. The cooling systems failed due to a lack of power. The cores of 3 reactors experienced a meltdown. Hydrogen gas accumulated and detonated, causing damage to the reactor buildings. Radiation found its way into the environment. Approximately 160,000 individuals were evacuated. The process of cleanup is expected to span decades. However, there is a remarkable detail. In the wake of the disaster, it is noteworthy that no fatalities have been directly linked to radiation exposure resulting from the incident. The evacuation itself brought about the most significant health impact, manifesting as psychological stress. This does not diminish the seriousness of the incident. The Fukushima incident was a significant nuclear disaster, yet it also illustrates that even in the face of multiple safety system failures, and even when the most dire situations arise, contemporary reactor designs exhibit remarkable resilience. The repercussions, though considerable, remain within the realm of control. Contrast these incidents with the everyday fatalities associated with alternative energy sources. Every year, thousands lose their lives in accidents related to coal mining across the globe. The impact of air pollution resulting from fossil fuel combustion leads to the loss of millions of lives each year. Hydroelectric dams have experienced catastrophic failures, such as the Banqiao Dam disaster in China in 1975, which resulted in an estimated loss of 171,000 lives. Nuclear power, despite its reputation, boasts one of the most impressive safety records in the energy sector. For each unit of energy produced, it results in a lower number of fatalities compared to coal, oil, gas, or even hydroelectric sources. It is important to acknowledge that nuclear power carries its own set of risks. It can be stated that those risks are manageable, well understood, and minor when compared to the risks of alternatives. Moreover, the latest reactor designs offer enhanced safety features. Modern reactors feature passive safety systems that operate independently of power or human involvement. In the event of cooling loss, the circulation of coolant is driven by natural convection and the force of gravity. When pressure accumulates, the relief valves engage automatically. In the event of a worst-case scenario, should the core melt, it is securely held within a specially engineered core catcher. Small modular reactors, currently under development, are designed to be simpler, featuring fewer components that may fail. Factory-built structures can be transported to various sites, leading to a reduction in construction costs and an enhancement in quality control. The future of nuclear power may not be confined to large, centralized plants. Smaller, distributed reactors could emerge as a source of power for towns and cities, working alongside renewable energy sources to deliver dependable, carbon-free electricity. It is essential to keep that context in mind. The reality of climate change is undeniable. It is unfolding. It is essential to seek energy sources that do not emit carbon dioxide. Nuclear power stands out as one of the rare technologies available today, capable of generating substantial electricity while producing no carbon emissions. Each kilowatt-hour produced by nuclear energy represents a kilowatt-hour that is not derived from the combustion of coal or gas. It is a kilowatt-hour that plays no part in heating the Earth. In a world grappling with the challenge of climate change, this holds significance. Now let us delve into a subject that feels more personal and may hold greater significance for you. Let us discuss the impact of radiation on living tissue. This understanding unveils the complexities surrounding the risks and the strength inherent in life. As radiation traverses the body, it engages with the atoms within the cells. High-energy photons or particles have the ability to dislodge electrons from atoms, resulting in the formation of ions. That is the reason it is referred to as ionizing radiation. It transforms atoms into ions. When ionization occurs in water molecules, which constitute roughly 60% of the human body, it leads to the formation of reactive molecules known as free radicals. Nearby molecules, including DNA, can suffer damage from these free radicals. The genetic code serves as the guiding blueprint for cellular function. It is composed of a code formed by 4 chemical letters, and the arrangement of these letters dictates every aspect of cellular function. Disruption of those instructions can occur due to damage to DNA. However, this is the essential point. The cells possess intricate systems dedicated to repairing DNA damage. Enzymes are perpetually on the lookout within your DNA, seeking out any errors and breaks that may exist. Upon discovering damage, they remove the affected section and reconstruct it, using the intact strand as a guide. The repair process demonstrates remarkable efficiency. Each day, countless DNA lesions occur in every cell of the body, arising from a multitude of sources, including natural metabolic processes, background radiation, and environmental chemicals. And each day, the repair systems address almost all of them. Problems arise only when damage becomes so extensive that the repair systems can no longer keep pace, or when errors manage to slip through and become integrated into the DNA sequence. When a cell gathers excessive damage, it usually leads to one of 2 outcomes. Either the cell initiates programmed cell death, effectively choosing to sacrifice itself for the greater good of the organism, or it halts its division indefinitely, entering a phase known as senescence. Each of these outcomes serves a protective purpose. They stop damaged cells from replicating further, thus reducing the risk of them turning cancerous. Yet, on occasion, a compromised cell defies its fate, continuing to divide instead of succumbing to its demise. Instead, It persists in replicating even while harboring mutations. If mutations impact the genes responsible for regulating cell growth, it could lead to the cell dividing without restraint. That marks the onset of cancer. This explains how exposure to radiation can elevate the risk of developing cancer. The number of DNA lesions rises, heightening the likelihood that certain lesions will evade the repair mechanisms, ultimately resulting in mutations that may lead to cancer. Yet, observe the layers of safeguarding. Ionization must occur within the appropriate molecule. That molecule must be DNA. The damage must remain unrepaired. The mutation must take place in a gene that influences cell growth. The cell must navigate the delicate balance of evading its own demise. And all of this must occur within a cell that can persistently divide. The sequence of improbable occurrences is extensive, which explains why even a moderate level of radiation exposure does not ensure the development of cancer. It marginally enhances the likelihood. The relationship between dose and cancer risk is complex and still not fully understood, especially at low doses. In cases of high doses administered swiftly, such as those experienced by atomic bomb survivors or victims of radiation accidents, we possess clear data. The likelihood of developing cancer rises with the amount of exposure in a generally straightforward manner. Increase the amount, and you significantly elevate the danger. However, when it comes to low doses administered gradually over an extended period, the situation becomes less clear. Some studies suggest that low-dose radiation may indeed stimulate protective mechanisms in cells, a phenomenon known as radiation hormesis. The idea is that small amounts of damage trigger an adaptive response that makes cells better at repair. Other studies find no protective effect. They suggest that even low doses carry some risk, albeit very small risk. The scientific consensus used for regulatory purposes is to assume a linear no-threshold model. This means we assume that any amount of radiation carries some risk proportional to the dose, with no threshold below, which there's no risk at all. This assumption is conservative. It's designed to be protective, but it might not reflect the true biological reality at very low doses. What we can say with confidence is that at the levels of radiation exposure most people experience in daily life, the risk is vanishingly small. Natural background radiation, medical X-rays, cosmic rays from air travel, all of these contribute doses that are far too low to cause detectable health effects in individuals. Think about it this way. If you receive an extra 1 millisievert of radiation exposure in a year, which is roughly the dose from a couple of chest X-rays or from living at high altitude, your lifetime cancer risk might increase by about 0.005%. That's 5 inches 100,000 or 1 inch 20,000. To put that in perspective, your lifetime risk of developing cancer from all causes is already about 40% or 400 out of 1,000. Adding 1 inch 20,000 to that is a change so small it's impossible to measure directly. This is why radiation workers, who receive more exposure than the general public, don't show dramatically elevated cancer rates. They're monitored carefully, their doses are kept below regulatory limits, and the small increased risk they face is accepted as part of their occupation, just as construction workers accept some risk of falls or drivers accept some risk of accidents. Let's drift now to a different aspect of radiation's interaction with life. Let's talk about adaptation, evolution, and the surprising ways that life has learned to cope with and even exploit radiation. Some organisms are remarkably resistant to radiation. The bacterium, Deinococcus, radiodurans, can survive radiation doses thousands of times higher than would kill a human. It's been called Conan, the bacterium for its toughness. How does it survive? It has multiple copies of its genome, allowing it to reconstruct its DNA from fragments after massive damage. It has highly efficient DNA repair enzymes, and it has cellular mechanisms that protect proteins from radiation damage. This organism wasn't engineered in a lab. It evolved naturally, probably in environments with naturally high radiation or other sources of DNA damage, like extreme dryness. Its radiation resistance is a byproduct of adaptations to harsh conditions. Fungi have been found growing on the walls of the destroyed reactor at Chernobyl. These fungi contain melanin, the same pigment that darkens human skin. Melanin appears to help protect the fungi from radiation, possibly by absorbing energy or by scavenging free radicals. Some researchers have even suggested that these fungi might be able to harness radiation for energy, though this claim is controversial and not yet proven. The point is that life is resilient. Life adapts. Life finds ways to survive in conditions we might think impossible. Even in humans, there's evidence of adaptation to radiation. People living in areas of high natural background radiation, like Ramsar or Kerala, don't just survive. Their cells show enhanced DNA repair capacity. It's as if exposure to slightly elevated radiation has selected for better repair mechanisms or has triggered adaptive responses that make their cells more resilient. This doesn't mean radiation is good for you. It means that life, including human life, has remarkable capacity to cope with environmental challenges. Let's think about radiation from an even broader perspective. Let's think about its role in evolution itself. Cosmic rays and natural radioactivity cause random mutations in DNA. Most mutations are harmful or neutral, but occasionally a mutation is beneficial. It gives an organism some advantage, some edge in survival or reproduction. Over millions of generations, beneficial mutations accumulate. Harmful ones are weeded out by natural selection, and gradually, organisms change. They evolve. Without mutations, evolution couldn't happen. Without some source of random changes to DNA, life would be stuck, unable to adapt to changing environments. Radiation is one source of those mutations. It's been contributing to genetic diversity, driving evolution for billions of years. In a very real sense, you exist because of radiation. The mutations that led to the evolution of complex cells, of multicellular organisms, of vertebrates, of mammals, of primates, of humans. Many of those mutations were caused by natural radiation. Your ancestors survived cosmic rays and radioactive potassium and radon gas seeping from the ground. They survived, they reproduced, and they passed on their genes, including the DNA repair mechanisms that made survival possible. You are the product of billions of years of life adapting to a naturally radioactive environment. Radiation is part of your heritage. Now, I want to talk about something that might help put radiation risk in an even clearer perspective. Let's talk about the concept of equivalent risk, because comparing radiation to other risks we face daily can be illuminating. Receiving a dose of 1 millisievert of radiation increases your lifetime cancer risk by about 1 inch, 20,000, as I mentioned before. But what else carries similar risk? Smoking 1 cigarette increases your cancer risk by about 1 inch, 20,000. Drinking 2 ounces of alcohol carries roughly similar risk. Being 10 pounds overweight increases your risk of heart disease by a similar amount. Driving 1,500 miles in a car, you have about a 1 inch, 20,000 chance of a fatal accident. Living in New York City instead of the countryside exposes you to air pollution that carries similar risk. Eating a charcoal grilled steak with its polycyclic aromatic hydrocarbons carries tiny cancer risk. Drinking coffee with its complex mix of chemicals, including some known carcinogens, carries tiny risk. The point isn't that all these things are equally dangerous. The point is that life is full of tiny risks. Every choice you make, every breath you take, carries some infinitesimal probability of harm. We accept these risks because the alternative is impossible. We can't live in a risk-free world. We can only try to minimize risks that are significant and accept risks that are negligible. Radiation exposure at low levels falls into the category of negligible risk. It's real, but it's tiny, and it's usually outweighed by the benefits of whatever activity is causing the exposure. getting a dental X-ray to check for cavities. The radiation risk is negligible compared to the benefit of detecting dental problems early. Flying across the country to family, the increased cosmic ray exposure is negligible compared to the joy of seeing loved ones. Living in a house with granite countertops, the radiation is negligible, period. There's no comparison needed because the risk is so small, it's essentially unmeasurable. Let's drift now to a more philosophical space. Let's think about why radiation causes such fear, despite its relatively modest actual danger. I think it's partly because radiation is invisible. You can't see it, smell it, taste it, or feel it. This invisibility makes it seem mysterious and uncontrollable. It's also partly historical. The atomic bombings of Hiroshima and Nagasaki, the Cold War fear of nuclear annihilation, images of mushroom clouds and fallout shelters, all of these created a cultural association between radiation and catastrophe. And it's partly because radiation represents human hubris. We split the atom. We harnessed forces that power the stars. And then we saw the consequences. Weapons capable of destroying cities, accidents at power plants, waste that remains hazardous for millennia. It seems like we've meddled with forces we can't control. But here's another perspective. Radiation is natural. It's ancient. It's fundamental to the universe. We didn't create it. We just learned to use it for better and worse. And our track record, while imperfect, is actually pretty good. We've used radiation to diagnose and treat diseases. We've used it to generate clean electricity. We've used it to understand the structure of matter and the history of the cosmos. Yes, we've also made weapons with it. Yes, we've had accidents, but we've learned from those mistakes. We've developed safety standards. We've created international agreements to prevent proliferation. We've built better reactors and disposal methods. The story of radiation is, in many ways, the story of human learning. We discover something new. We experiment with it. We make mistakes. We learn. We improve. We try to do better. And all the while, the natural radiation that has always surrounded us continues its quiet work, transforming atoms, carrying energy, shaping the universe at scales, both cosmic and quantum. Let me tell you about some of the beautiful ways radiation has helped us understand the world. Radiocarbon dating uses the decay of carbon-14 to determine the age of ancient objects. When an organism is alive, it constantly absorbs carbon-14 from the atmosphere through food and respiration. When it dies, the absorption stops, and the carbon-14 begins to decay with a half-life of 5,730 years. By measuring how much carbon-14 remains in a sample, scientists can calculate how long ago the organism died. This technique has revolutionized archaeology and paleontology, allowing us to date artifacts, fossils, and geological events with remarkable precision. The Dead Sea Scrolls were dated using radiocarbon analysis. The age of the Turin Shroud was determined this way. Ancient civilizations, extinct species, climate changes from tens of thousands of years ago, all revealed through the gentle decay of carbon atoms. Other radioactive isotopes allow us to date much older materials. Uranium decays into lead with a half-life of billions of years, allowing geologists to date rocks and determine the age of Earth itself. That's how we know our planet is about 4.54 billion years old. The oldest rocks ever found on Earth, in northwestern Canada, are about 4.03 billion years old, dated using uranium-lead dating. The oldest minerals, zircon crystals from Australia, are about 4.4 billion years old. These tiny grains of crystal, dated using the decay of radioactive uranium, tell us that Earth had solid crust and probably liquid water within a few 100 million years of its formation. They tell us the story of our planet's early history, written in the decay of atoms. Radiation has also given us medical treatments that save lives. Radiation therapy for cancer uses high-energy radiation to damage the DNA of cancer cells, killing them or preventing them from dividing. It sounds harsh, and in a sense, it is. Radiation therapy is a controlled use of radiation's destructive power, but cancer cells, which divide rapidly, are more vulnerable to radiation damage than most normal cells. And modern techniques can focus radiation beams with incredible precision, targeting tumors while minimizing exposure to surrounding healthy tissue. Intensity-modulated radiation therapy uses computer-controlled beams that can be shaped to match the three-dimensional form of a tumor. The radiation is delivered from multiple angles, with each beam alone being too weak to cause significant damage, but all beams combined, delivering a therapeutic dose to the tumor. Proton therapy uses beams of protons instead of photons. Protons deposit most of their energy at a specific depth, determined by their initial energy. This allows even more precise targeting of tumors, with less damage to surrounding tissue. These techniques have cured countless cancers. They've extended lives, they've reduced suffering. And they exist because we learn to understand and control radiation. Radioactive isotopes are also used as tracers in medicine. Technetium-99 meters is a radioactive isotope with a half-life of 6 hours. It's attached to various molecules that accumulate in specific organs or tissues. Patients are injected with tiny amounts of these tracers, and a special camera detects the gamma rays emitted by the technetium, creating images of bones, hearts, kidneys, or other organs. These nuclear medicine scans can detect tumors, blood clots, infections, and organ dysfunction. The radiation dose is small, typically a few millisieverts, and the information gained can be life-saving. After the scan, the technetium decays quickly. Within a day, most of it is gone. Within a week, it's undetectable. The patient returns to their normal background radiation level, carrying no lasting radioactivity. Radiation has also been used in sterilization of medical equipment. Gamma rays from cobalt-60 can penetrate plastic packaging and kill bacteria, viruses, and other pathogens without damaging the equipment inside. Syringes, surgical gloves, bandages, and countless other single-use medical supplies are sterilized this way. This allows for sterile, disposable equipment, which has dramatically reduced infections in medical settings. Before sterilization techniques became widespread, hospitals were dangerous places where infections spread easily. Now, thanks in part to radiation sterilization, they're much safer. In agriculture, radiation has been used to create new crop varieties through mutation breeding. Seeds are exposed to gamma rays or other radiation sources, causing random mutations. Most mutations are harmful, and the seeds don't grow. But occasionally, a mutation produces a beneficial trait: disease resistance, higher yield, better flavor, improved nutrition. These mutant plants are selected and bred traditionally to create new varieties. More than 3,000 varieties of crops have been developed this way, including rice varieties that feed millions, wheat that's resistant to drought, and barley used in brewing beer. This isn't genetic engineering in the modern sense. No genes are inserted from other organisms. It's simply accelerated mutation, using radiation to speed up the process that would happen naturally over many generations. The food you eat might include products from mutation breeding, and you'd never know it. The technique is accepted worldwide and considered safe because the final product doesn't contain any radiation and is genetically stable. Now let's think about radiation in space. Because beyond Earth's protective atmosphere and magnetic field, radiation becomes a more significant concern. Astronauts on the International Space Station, orbiting about 400 kilometers above Earth, receive about 150 millisieverts of radiation per year. That's about 50 times higher than the average person on Earth's surface. They're exposed to cosmic rays from outside our solar system, solar protons from the sun, and particles trapped in Earth's magnetic field. The space station's hull provides some shielding, but it's not perfect. High-energy particles can penetrate aluminum and create secondary particles when they collide with the hull material. Despite this elevated exposure, astronauts who spend 6 months on the space station don't show obvious health effects. Their cancer risk increases slightly, by perhaps 3% over their lifetime. NASA monitors their exposure carefully and sets career limits to keep lifetime risk below what's considered acceptable. For missions beyond Earth orbit, radiation becomes more challenging. Traveling to Mars, for example, would expose astronauts to deep space radiation for months with no protective magnetic field. The round trip to including time on the surface might expose astronauts to about 1 sievert of radiation, depending on solar activity and shielding. That's a significant dose, roughly equivalent to a lifetime of background radiation on Earth, compressed into 2 or 3 years. It would increase cancer risk noticeably, perhaps by 10 or 15%. It's not a trivial risk, but it's also not prohibitive. Many astronauts would accept that risk for the chance to explore another planet. And there are ways to reduce the risk. Better shielding, using water or hydrogen-rich materials, faster propulsion systems to reduce travel time, forecasting solar storms, and taking shelter during high radiation events. Underground habitats on Mars to reduce surface radiation exposure. Humanity will solve these problems because we want to explore. We want to extend our reach beyond this planet, and radiation, while a challenge, is a manageable one. Let's think now about the Sun, because our star is essentially a giant nuclear reactor, and understanding it helps us appreciate radiation's cosmic role. At the Sun's core, hydrogen nuclei fuse together under tremendous pressure and temperature to form helium. This fusion releases energy in the form of gamma rays, but those gamma rays don't immediately escape. They're absorbed by atoms in the dense solar interior and re-emitted at slightly lower energy. This happens over and over, with photons bouncing randomly through the Sun's interior, gradually losing energy, transforming from gamma rays to X-rays to ultraviolet to visible light. It takes about 100,000 years for energy created in the Sun's core to reach the surface. That photon you see when you look at the Sun started its journey during the Ice Age, when woolly mammoths still roamed Earth. When the light finally reaches the surface, it escapes into space and travels outward at the speed of light. 8 minutes and 20 seconds later, it reaches Earth. Some of it is absorbed by the atmosphere, some reaches the ground, some reaches you. That sunlight, that electromagnetic radiation spanning from ultraviolet through visible light to infrared, is what makes life on Earth possible. It provides the energy that plants use for photosynthesis. It warms the air and the oceans, driving weather and climate. It regulates our circadian rhythms and even helps our skin produce vitamin D. Without the Sun's radiation, Earth would be a frozen, lifeless rock. The oceans would freeze solid. The atmosphere would condense and fall as snow. Any life that had somehow emerged would quickly perish. So when you feel sunlight on your skin, remember that you're feeling radiation from nuclear fusion. You're feeling energy that was created by the same process that powers hydrogen bombs, but released gently, continuously, at a distance that makes it warming rather than destructive. The Sun also emits higher energy radiation, ultraviolet light, X-rays, and even gamma rays. Most of this is absorbed by Earth's atmosphere and magnetic field. The ozone layer absorbs ultraviolet. The ionosphere reflects radio waves. The magnetosphere deflects charged particles. These protective layers exist because Earth is geologically active, with a molten core generating a magnetic field, and because life itself has shaped the atmosphere. Early photosynthetic bacteria produced oxygen, which led to the formation of the ozone layer, which allowed complex life to colonize land. It's a beautiful, interconnected system. Radiation from space is filtered by Earth's natural defenses, allowing just enough through to sustain life while blocking the most harmful forms. Sometimes the Sun burps out extra radiation in the form of solar flares and coronal mass ejections. These events can temporarily increase radiation levels in space and even affect Earth's upper atmosphere, creating auroras, as charged particles interact with atmospheric gases. Auroras, those shimmering curtains of green and red light dancing across polar skies, are radiation in action. They're caused by electrons and protons from the Sun colliding with oxygen and nitrogen atoms in the upper atmosphere, exciting those atoms and causing them to emit light. People travel thousands of miles to see auroras. They're considered among the most beautiful natural phenomena on Earth, and they're the visible manifestation of space radiation, interacting with our atmosphere. Now let's return to Earth and think about radon, because radon is the single largest source of radiation exposure for most people, and yet it's poorly understood. Radon is a noble gas, element 86 on the periodic table. It's produced by the radioactive decay of uranium and radium in rocks and soil. As it's produced, it seeps upward through cracks and pores in the ground, eventually reaching the surface. In open air, radon disperses and becomes diluted to very low concentrations. But if it seeps into a building, it can accumulate, especially in basements and ground floors, where ventilation is poor. Radon itself is radioactive, with a half-life of about 4 days. It decays into a series of other radioactive elements called radon progeny, which are solid particles that can attach to dust or be inhaled directly. When you breathe in radon and its progeny, they decay in your lungs, releasing alpha particles. These alpha particles can't penetrate far, but they don't need to. They're already inside your lungs, in direct contact with lung tissue. Over years or decades of exposure to elevated radon levels, this can increase lung cancer risk. Radon is the second leading cause of lung cancer after smoking, responsible for about 21,000 deaths per year in the United States. But here's what's important. Radon risk is highly variable. Some homes have very low radon levels, barely above outdoor air. Others have high levels, hundreds of times higher than average. The only way to know your radon level is to test. Test kits are inexpensive and easy to use. You place a detector in your home for a few days or months, send it to a lab, and get back of the average radon concentration. If the level is high, above 4 picocuries per liter, a standard used in the US, you can take steps to reduce it. Sealing cracks in the foundation helps. Improving ventilation helps. Installing a radon mitigation system, which uses a fan to draw radon from beneath a house and vent it outside, can reduce levels by 90% or more. The point is that radon, while a significant source of radiation exposure, is manageable. You can test for it. You can reduce it. You can make informed decisions about whether mitigation is worthwhile based on your specific situation. Many people live in homes with elevated radon and never know it because they never test. They breathe it for decades and might never develop lung cancer, because cancer from radon, like cancer from any cause, is probabilistic, not certain. But testing empowers you. It gives you information. And information allows you to make choices that might reduce your risk. Before we move forward, let's pause for a moment to appreciate something truly remarkable. Every single second of every single day, about 7,000 cosmic ray particles pass through your body. These particles have journeyed across the galaxy, some of them traveling for millions of years through the vacuum of space before encountering you. Each one carries a story, written in its energy and trajectory. Some come from the sun, accelerated by solar flares. Others come from supernova remnants, the expanding shells of gas and radiation from stars that exploded before humans evolved. Still others come from beyond our galaxy, from active galactic nuclei powered by supermassive black holes, from pulsars spinning hundreds of times per second, from sources we haven't yet identified, and they pass through you as if you were transparent, which, at their energy scales, you essentially are. Your body is mostly empty space at the atomic level, and these high-energy particles slip between atoms, through atoms, barely noticing your existence. Occasionally, maybe once every few minutes, one of these particles will strike a nucleus in one of your cells. The collision creates a brief shower of secondary particles. Energy is deposited, molecules are ionized, and then, within seconds or minutes, your cellular repair mechanisms identify and fix the damage. This has been happening since before you were born. It happened to your parents, your grandparents, your ancestors, stretching back millions of years. Every human who has ever lived has faced this relentless onslaught of cosmic radiation. It constitutes an essential aspect of the human experience on this planet. The ability of life to not only endure but flourish in the face of adversity highlights the remarkable resilience inherent in biological systems. People often underestimate their own resilience. The cells engage in a relentless vigilance, perpetually scanning for any signs of damage, tirelessly executing repairs, and steadfastly upholding the integrity of our genetic code amidst a myriad of challenges, with radiation being merely one among many. Grasping this notion can bring a peculiar sense of solace. You are designed to withstand radiation. The essence of your biology has undergone scrutiny through the vast expanse of billions of years of existence. The systems that safeguard your well-being against natural radiation are the very same systems that protect you from a multitude of other adversities. In a profound way, one can say that you are shaped by the influence of radiation. The mutations that propelled evolution were, in part, influenced by radiation. The selection pressures that influenced the ancestors included their capacity to mend radiation damage. Your existence is a testament to the resilience of your ancestors, who thrived in a world shaped by radiation for countless ages. This heritage is inscribed within your DNA, woven into the repair enzymes that safeguard your genome, embedded in the cellular checkpoints that identify damage, and integrated into the programmed death pathways that eliminate compromised cells to preserve the integrity of the entire organism. They are descended from survivors, carrying the adaptations of their ancestors within them. Consider the topic of radiation in food, as it often raises concerns, yet reveals fascinating insights upon closer examination. Bananas are a source of potassium, and as previously mentioned, a small portion of this natural potassium is the radioactive isotope potassium-40. A typical banana holds approximately 450 milligrams of potassium, which comprises around 0.017% potassium-40. This indicates that a banana produces approximately 15 radioactive decays every second. Researchers humorously describe the banana equivalent dose as a casual method to convey minor levels of radiation exposure. Consuming a banana exposes you to approximately 0.001 millisieverts of radiation dose. However, this is where it becomes intriguing. The body meticulously manages its potassium levels. As one consumes a banana, potassium is absorbed into the body, yet simultaneously, potassium is excreted to uphold a state of balance. The radioactive potassium found in a banana does not notably elevate the overall radioactive potassium levels in your body. Although bananas are indeed radioactive, consuming them does not significantly elevate your radiation exposure. The radioactive potassium content of the body remains largely unchanged. Other foods also possess radioactivity. The Brazil nut trees, with their roots delving deep into the earth, absorb radium and other radioactive elements, leading to a notable level of radioactivity in the nuts they produce. A solitary Brazil nut may hold tenfold the amount of radium compared to the potassium-40 found in a banana. Does this imply that Brazil nuts pose a risk? No, the quantity remains minimal. One would have to consume a significant amount of Brazil nuts each day over an extended period to accumulate enough radiation to present any health concerns. Long before radiation emerged as a concern, individuals encountered various health issues stemming from excessive consumption. It is important to recognize that radiation in food is a natural and widespread phenomenon. Every morsel you consume holds within it tiny traces of radioactive isotopes. The body manages this with ease, a testament to our evolution alongside radioactive sustenance. In contemplating evolution, one might consider the significance of radiation in the formation of elements, as this represents a deeply profound and beautiful facet of radiation's cosmic narrative. At the outset, the universe was composed solely of hydrogen and helium, accompanied by faint hints of lithium. In the vast cosmos, all the heavier elements, spanning from carbon to uranium, came into existence within the hearts of stars, forged through the intricate dance of nuclear fusion and various other processes. Within the hearts of stars, hydrogen transforms into helium. Helium evolves into carbon and oxygen, and the process continues up the periodic table. With each fusion, energy is released, radiating outward in the form of light. However, fusion is limited to the creation of elements, only up to iron. Beyond iron, fusion requires energy instead of releasing it, which is why it does not occur during typical stellar burning. The elements that surpass iron in weight are forged in the cataclysmic explosions of supernovae and other extraordinary occurrences. As a massive star meets its explosive end, the immense energy and neutron flux facilitate a swift process of neutron capture, leading to the formation of heavy nuclei that subsequently undergo radioactive decay into stable forms. Every atom of gold, silver, platinum, lead, and uranium originated from a stellar explosion that occurred billions of years ago. These atoms were propelled into the cosmos, mingling with gas and dust, ultimately becoming part of new stars and planets, including Earth. The gold in a wedding ring, the uranium in a nuclear reactor, and the lead in a car battery. All were shaped in the final moments of ancient stars' existence. The process that brought them into existence involved radioactive decay, with unstable isotopes transitioning into stable forms. As you adorn yourself with jewelry or manipulate heavy metals, you engage with atoms that have traversed the cosmos, embodying a narrative that stretches across eons. Some of those atoms remain radioactive, continuing their slow decay, quietly releasing the final echoes of energy from their tumultuous origins. It evokes a sense of humility and beauty. Humanity is composed of stardust, with remnants of that stardust still emitting a faint glow from its ancient radioactivity. Let us now shift our perspective to consider radiation in medicine from an alternative viewpoint. Let us explore diagnostic nuclear medicine and the way radioactive tracers can uncover the intricate functions of the human body. PET scans, known as positron emission tomography, utilize positron-emitting radioactive isotopes to generate three-dimensional images that reveal the metabolic processes occurring within the body. A frequently used tracer is fluorine-18, which is bonded to a glucose molecule, resulting in a compound known as FDG. Upon being injected into a patient, this radioactive glucose is taken up by cells in the same manner as regular glucose. Metabolically active cells, such as cancer cells, or regions of the brain that are engaged in activity, take in greater amounts of it. The fluorine-18 undergoes decay, releasing a positron into the surroundings. Upon the encounter of a positron and an electron, they meet their end in a dramatic annihilation, transforming their mass into two gamma rays that swiftly dart away in opposite directions. The PET scanner identifies the gamma rays, utilizing their timing and direction to ascertain the location of the annihilation event. Through the aggregation of countless events, a computer creates a visualization that reveals the areas where radioactive glucose has gathered. This enables physicians to visualize tumors, to determine if cancer has disseminated, and to gauge the effectiveness of treatment. This enables neuroscientists to observe the regions of the brain that engage during various activities. It serves as a glimpse into the vibrant, operating essence of life. The radiation dose from a PET scan ranges from approximately 5 to 7 millisieverts, which is similar to the amount of background radiation one would be exposed to over a couple of years. The fluorine-18 possesses a half-life of approximately 110 minutes, leading to its rapid decay. In the span of a single day, it has all but vanished. The insights acquired, however, can prove to be priceless. A PET scan has the ability to identify cancer at an earlier stage compared to other imaging techniques. It has the ability to differentiate between scar tissue and an active tumor. It has the potential to influence treatment choices that preserve lives. Another captivating application of radiation in medicine is radioimmunotherapy, a process in which radioactive isotopes are linked to antibodies designed to seek out particular cancer cells. The antibodies pursue the cancer cells, attaching themselves to the tumors and administering radiation directly, all the while preserving the surrounding healthy tissue. This resembles a precision-targeted molecular missile. The antibody serves as a guiding force, locating the cancer cells with precision. The warhead is powered by a radioactive isotope, unleashing cell-killing radiation with remarkable accuracy. The field is still developing, yet it holds potential for addressing specific cancer types, especially lymphomas and leukemias, where cancer cells move through the bloodstream and are challenging to reach with traditional radiation treatments. The existence of these medical applications stems from our fundamental understanding of radiation. It is understood how various isotopes undergo decay. The interaction of radiation with tissue is well understood. The ability to calculate doses and predict effects is well understood. Radiation, once an enigmatic force, has been transformed into a valuable medical instrument. Now let us consider radiation through a more artistic lens, as it has sparked inspiration in art, literature, and culture in intriguing manners. The discovery of radium and its eerie glow captivated the public's imagination during the early 20th century. Radium found its way into the market as a health product, incorporated into toothpaste, cosmetics, and even drinking water, driven by a misguided belief in the benefits of radioactivity. In a time when innovation met peril, young women known as radium dial painters meticulously applied radium-infused paint to watch faces, ensuring that the numbers would emit a luminous glow in the dark. The paint was described to them as harmless. They received guidance to moisten their brushes with their tongues to preserve a sharp tip. Years later, many of these women found themselves grappling with illnesses brought on by radiation exposure. Their tale is one of tragedy, yet it paved the way for significant progress in occupational safety and radiation protection. Their suffering held a deeper significance. It imparted lessons that safeguard workers in the present day. The allure of radiation, with its glowing green substances and enigmatic rays, found its way into the fabric of popular culture. In the realm of science fiction, radiation emerged as a catalyst for extraordinary abilities and unforeseen transformations. Films portrayed colossal ants and lizards, spawned from atomic experiments. These cultural artifacts, despite their scientific inaccuracies, mirrored profound anxieties surrounding nuclear technology and the atomic age. Their reflections captured both awe and trepidation regarding the unseen powers that humanity had come to harness. In contemporary art, the portrayal of radiation has evolved to reflect a deeper complexity. Films such as Chernobyl reveal the profound human impact of nuclear disasters, all the while honoring the intricate nature of the science involved. Artists have crafted installations that utilize real radiation detectors, transforming the unseen into a tangible experience through sound and light. Radiation holds a depth of philosophical significance. It exists in a tangible form, quantifiable and regulated by exact scientific principles, yet remains entirely beyond the reach of human perception. It functions at levels that elude our immediate awareness, existing within the domain of atoms and subatomic particles. This positions radiation as an ideal symbol for the unseen influences that mold our reality. Gravity, magnetism, and quantum fields function below the limits of direct perception, yet they play a crucial role in shaping the essence of reality. Grasping the concept of radiation becomes a journey that broadens our perception beyond what is immediately apparent. It involves developing a reliance on instruments and mathematics to uncover truths that elude our senses. Consider the philosophy of radiation protection, as the approach to radiation safety unveils intriguing insights into risk management and societal perspectives. The core tenet of radiation safety is to keep exposure as minimal as possible within reasonable limits. This suggests that even when radiation exposure falls within regulatory limits, efforts should still be made to minimize it further, provided it can be achieved without significant expense or hardship. This approach is cautious and measured. It posits that all radiation entails a degree of risk. Thus, prioritizing the reduction of exposure is consistently advisable. However, it also recognizes that complete avoidance of exposure is unattainable, and that we must weigh radiation protection alongside other considerations. For instance, lead aprons utilized during X-rays offer protection, yet they are cumbersome and uncomfortable. When undergoing a quick dental X-ray, the use of a lead apron diminishes an already minimal dose to an even lesser extent. The advantage is slight, yet the drawback, enduring discomfort for a brief moment, is equally minimal. Thus, it is done. However, for extended procedures, the importance of comfort and mobility may take precedence. A surgeon engaged in a complex procedure under X-ray guidance may opt against wearing full lead protection if it could hinder their capacity to conduct the surgery safely. The marginal rise in radiation exposure is deemed acceptable, as the alternative compromised surgical performance presents a far greater risk to the patient. This type of intricate evaluation of risks and benefits is perpetually utilized in the realm of radiation protection. It acknowledges that radiation represents merely one among numerous risks we encounter, and that reducing radiation while neglecting other significant objectives isn't necessarily the best decision. Another principle is justification. Every practice that entails exposure to radiation requires justification, signifying that the advantages must surpass the potential hazards. A diagnostic X-ray is warranted when it is expected to yield valuable insights. The justification falters when the same information can be acquired without the use of radiation, or when such information is deemed unnecessary. This explains the reason behind doctors inquiring about past imaging prior to requesting new scans. This is the reason children are given smaller doses compared to adults, and why pregnant women are questioned about their pregnancy status prior to undergoing X-rays. Every exposure requires justification rooted in the unique circumstances at hand. The third principle revolves around the concept of optimization. In any situation where exposure is warranted, it is essential to optimize the dose to attain the desired result, while minimizing exposure to the lowest feasible level. This explains the reason contemporary X-ray machines utilize digital detectors, which necessitate a lower amount of radiation compared to film. The purpose of dose reduction algorithms in CT scanners is to enhance patient safety while maintaining image quality. Nuclear medicine often opts for isotopes that have short half-lives when feasible. Each technical advancement that lowers dosage while preserving or enhancing image quality exemplifies the essence of optimization at work. The principles of ALARA, justification, and optimization serve as the cornerstone of contemporary radiation protection. They are implemented globally, safeguarding countless individuals from unwarranted exposure, while still permitting the advantageous applications of radiation to persist. Let us shift our focus to the vastness of the cosmos and contemplate radiation within the expansive universe, as it serves as the fundamental means through which we gain insights into objects that lie beyond our reach. When one gazes at the stars, one is witnessing their radiation. The light that reaches your eye embarked on its journey from those stars years, decades, centuries, or even millennia ago, influenced by the vastness of distance. Some stars visible to us are so far away that the light we see today started its journey long before the dawn of human civilization. However, visible light represents merely a small fraction of the entire electromagnetic spectrum. Stars are known to emit a variety of waves, including radio waves, infrared, ultraviolet, X-rays, and gamma rays. Through the observation of various forms of radiation, astronomers are able to ascertain a star's temperature, composition, age, and motion. The analysis of radiation across various wavelengths unveils the elements present in distant objects. Every element interacts with radiation in a distinct manner, absorbing and emitting it at specific wavelengths, which results in a unique spectral signature. Through the analysis of starlight, it becomes possible to ascertain that a star located billions of light-years away is composed of hydrogen, helium, carbon, iron, and various other elements. The temperature can be measured with an accuracy of a few degrees. The velocity of the object, whether it is moving toward us or away, can be determined by analyzing the Doppler shift of its spectral lines. All this arises from radiation, from photons that have journeyed across immense distances, bearing information intricately encoded in their wavelengths and intensities. Radiation enables us to penetrate dust clouds that would typically block visible light. Infrared radiation cuts through dust, enabling astronomers to witness the hidden regions of star formation concealed within gas clouds. Radio waves effortlessly penetrate dust, enabling the mapping of hydrogen gas distribution across the galaxy and beyond. X-rays unveil intense energy phenomena, such as matter descending into black holes or neutron stars. Gamma rays reveal the most tumultuous occurrences in the universe. Supernovae, gamma-ray bursts, and matter-antimatter annihilation unfold in a grand cosmic narrative, revealing layers of significance and intrigue. Every type of radiation offers a unique perspective of the universe. Collectively, they provide a detailed understanding of the universe's framework and its development over time. All of this hinges on the same essential phenomenon that has been the focus of our discussion. Radiation remains radiation, regardless of whether it originates from a light bulb, a radioactive atom, or a far-off quasar. The principles remain unchanged. The principles of physics apply universally. Consider the future of radiation, science, and technology, as ongoing advancements consistently enhance our comprehension and utilization. Investigations into the effects of low-dose radiation persist, seeking to clarify whether minimal exposures pose any risk, or could potentially offer benefits through hormetic effects. Extensive research involving radiation workers, medical patients, and communities exposed to high levels of background radiation offers valuable insights. However, conclusive answers continue to evade us, as the potential effects, if present, are exceedingly minor. Innovative reactor designs offer the potential for enhanced safety compared to existing plants. Molten salt reactors utilize liquid fuel that can flow into passively cooled tanks in the event of excessive temperature increases. Traveling wave reactors have the capability to utilize depleted uranium and nuclear waste. Small modular reactors possess the ability to be mass-produced and can be situated with great flexibility. Some designs utilize thorium in place of uranium as fuel. Thorium is found in greater quantities than uranium and generates a smaller amount of long-lived waste. Thorium reactors present challenges in the production of weapons materials, thereby alleviating concerns about proliferation. The pursuit of fusion power, the very process that fuels the sun, continues to be a challenging aspiration. For decades, scientists have dedicated their efforts to the pursuit of controlled fusion, striving to contain and heat hydrogen isotopes until they reach the necessary conditions for fusion, thereby releasing energy. Recent advances indicate that fusion power could potentially become a practical reality in the decades ahead. In France, a massive experimental reactor is being constructed as part of the ITER project. Private companies are exploring compact, more inventive designs. Should fusion achieve success, it has the potential to deliver plentiful clean energy while generating minimal radioactive waste. The fuel, deuterium, and tritium is capable of being extracted from seawater. The main byproduct is helium, an entirely benign gas. Fusion does not completely eliminate radiation. In fusion reactions, neutrons are generated that interact with the reactor structure, resulting in the activation of materials and rendering them radioactive. However, the induced radioactivity has a significantly shorter lifespan compared to fission waste, diminishing to safe levels within decades instead of millennia. In the realm of medicine, innovative techniques consistently come to light. Flash radiotherapy administers remarkably high doses of radiation in mere fractions of a second. Initial studies indicate that this ultra-fast delivery could potentially protect healthy tissue more efficiently than traditional radiation therapy. All the while, effectively targeting tumor cells. Theranostics merges the realms of diagnosis and therapy by utilizing a single molecule marked with various radioactive isotopes for both imaging and treatment purposes. For instance, a tracer for prostate cancer may initially utilize a short-lived isotope for imaging purposes, followed by the application of a longer-lived therapeutic isotope to provide treatment. Proton therapy facilities are increasingly prevalent, providing accurate tumor targeting while minimizing harm to adjacent tissues. This holds particular significance for childhood cancers, as it is essential to reduce radiation exposure to developing organs. In the realm of space exploration, nuclear power emerges as a viable solution for missions where solar power proves impractical. The Mars rovers have employed radioisotope thermoelectric generators, or RTGs, which transform heat generated from the decay of plutonium directly into electricity. RTGs have provided energy for spacecraft, venturing into the distant reaches of the solar system, where the sunlight is insufficient for solar panels to function effectively. The Voyager probes, having ventured into interstellar space for over 40 years since their launch, continue to function on nuclear power. Future missions to Jupiter's moon Europa or Saturn's moon Enceladus, where liquid oceans may conceal life, are expected to utilize nuclear power. The energy density of radioactive decay stands unparalleled when compared to chemical or solar alternatives for deep space missions. There is even a conversation surrounding nuclear thermal rockets, which would utilize a nuclear reactor to heat hydrogen propellant, offering significantly greater thrust compared to chemical rockets. These engines have the potential to cut the travel time to Mars from 9 months down to 3 or 4, greatly minimizing the crew's radiation exposure during the journey. The essence lies in the fact that our connection with radiation is in a constant state of transformation. New applications are continually being discovered, safety measures are being enhanced, and our understanding is being deepened. Tonight, the most important lesson about radiation is not how much of it surrounds you. It is how well modern science has learned to measure, predict, and manage invisible risk. Radiation teaches a quiet principle that reaches far beyond physics. Not all danger is loud, not all safety is visible. What truly protects human life is not fear, but systems of understanding. We learned how energy leaves atoms. We learned how distance reduces intensity. We learned how shielding changes exposure. We learned how biology repairs damage. And most importantly, we learned how to design rules that keep uncertainty small, even when the phenomenon itself cannot be seen. This is what science really does. It does not promise perfect safety. It creates decision frameworks. In medicine, radiation becomes a tool to detect disease early. In engineering, it becomes a controllable source of power. In space exploration, it becomes a design constraint rather than a barrier. In everyday life, it becomes a background condition that can be managed instead of feared. Understanding radiation is not about memorizing particles and units. It is about learning how modern societies handle invisible risks through measurement, modeling, and continuous improvement. And that same mindset quietly shapes many parts of your own world. Water quality, air pollution, food safety, structural engineering, medical screening, digital security, all of them rely on the same principle you have explored tonight. We cannot remove uncertainty from life, but we can design systems that prevent uncertainty from becoming harm. If this exploration felt useful, take one quiet moment before sleep to notice something simple in your own life. A detector, a warning sign, a safety standard, a protective routine. Behind each of them is the same scientific discipline you have just experienced. From all of us at Sleep Science Top 1, thank you for sharing this quiet journey into how invisible forces are understood, managed, and transformed into safety. Rest well, and let curiosity remain gentle.